All right, good afternoon. Next, we have the talk this afternoon. The speaker is Giulia Zanderighi, and she is awardee of the Frontiers of Science Award. And today he will talk about the photon PDF. Okay, please.
Okay, thank you very much. Can you hear me? Okay, thank you, yes. So today I will tell you a little bit about this, written in collaboration with Anish Manohar, Paolo Nasonna, and Gavin Salam. And it's about the photon content of the protons. Okay, so what is the context? Well, today we are running the Large Hadron Collider machine, and the protons in these LHC beams, so the beams are made of protons. These protons are charged moving particles. So one of the questions is, what is the electromagnetic field associated to these charged moving particles? Now, the same question was addressed by Fermi already in 1924, but he was talking about point-like charged particles, like electrons. So he was concerned with how do you relate the energy loss of electrons, charged particles, elementary charged particles that move in matter via the absorption of X-rays by atoms. This concept was then also further developed by Weizsäcker and Williams. They wanted to describe processes like Bremsstrahlung, and other phenomena still related to scattering of charged particles. And the approximation they use is what is now well known as the Weizsäcker-Williams approximation. The problem is that protons are not elementary particles, so things are a little bit more complicated than what I described. But, yeah. I would like to start by showing you this, the paper written by Fermi in 24. And some of this was written in German at the time, so this is a translation to English. And yeah, he was really concerned with the electric field associated with electrons, and the fact that you can somehow, the probability that atoms are excited for these electric fields can be somehow equated to the probability that the excitation you would have if you would have an equivalent photon radiation. But as I say, I mean, this was only in the context of elementary particles. Sorry, a bit confusing. Okay, so the fundamental question that was addressed in the paper is what is the electromagnetic field associated to protons, really? And why is this relevant? But it's relevant because any calculation, precision calculation we do for collider processes today relies on this essentially master formula. So this master formula tells you that any cross-section that you can measure at colliders can always be written in this form, where you have a partonic cross-section that typically involves elementary particles, quarks and gluons or photons. And this cross-section is convoluted with this function, which we call parton distribution functions. They can be thought of the probability to pick a quark or gluon in the proton with a given momentum fraction x at a given scale, this so-called factorization scale. So you have to integrate over this x1 and x2, integrate over the phase space for the final state, and then possibly have some cuts. But this formula is extremely general, is always used. And of course, here somehow these parton distribution functions involving quarks and gluons were very well known, but not the ones for photons. And I will explain a little bit what was really known and not. So what is the problem in describing photons from protons? Well, you can think about this, that you have scatterings, and you have different impact parameters in the scattering. So if the impact parameter is very large, effectively you can think of a proton as if it was a point-like particle, right? Because if you're very far away, you don't distinguish. So this regime, in this regime, we know how to compute the photon PDF of a proton. It is very similar to what you have for elementary point-like particles. But when the impact parameter decreases, when you somehow start probing the size of the protons, in this regime, so of the order of a femtometer, the size of a proton, you start probing the internal structure of the proton. And this is the region also where typically we can never do perturbative calculation. This is somehow a non-perturbative regime of strong coupling. When you go to even smaller distances, at these distances, you essentially probe the quarks and gluons in the proton as if they were free particles, point-like quarks or gluons. And at that point, you can again compute things in a perturbative way. You can talk about how a quark splits and emits a gluon. So somehow the first and third regime are the most easy ones. The second is the most complicated one, but to have a full result, to be able to make predictions in the whole range, essentially. Okay, so what was done before our work? Before our work, there were some model-independent fits of photon distribution functions. So in general, there are various groups, professional people that do these fits. And so the fit was really relying on data. And so it was relying essentially mostly on Drellian data from a low mass on-shell region close to the Z peak or very high mass, and also deep inelastic scattering data. So they somehow assumed an agnostic polarization, and then they were fitting the photon distribution function. So, and this is somehow the result of the fit that they obtained. So what I'm showing here is not really the photon distribution function, but luminosity for gamma-gamma interactions. So you assume that you have two photons and they produce an object of mass m. So this is the quantity of relevance if you want to compute a resonance produced by photon-photon scattering, essentially. And what you see that you can do this fit, you can obtain a result, but the uncertainty was really very large. So according to the mass that you're producing, you can have uncertainties a factor of 1,000 or at least a factor of 5 uncertainty. There were also other approaches. For instance, the MRST 2004 group produced a photon PDF. And so here they assumed essentially that the photon is radiated from quarks at some starting scale. So this starting scale is a free parameter. You don't have control of it. And then they somehow computed this evolution from the quarks, essentially. So this is what we would call the inelastic component. Our approaches combined this inelastic component with an elastic contribution where the photon the proton remains intact. And there was also a more recent approach, 2014, that essentially included some constraints on the effective mass under which you don't assume that you have photon radiation. The problem of this is that all these approaches have a model dependence. For instance, they have some parameters that you don't have control of. And so when you have such a strong model dependence, it becomes very difficult also to quantify the uncertainty that you have. And so this is a bit summarized in this table. So this was the status before our work. There were different groups have looked into the problem. They considered only the inelastic or both elastic and inelastic. If there was an elastic component, typically it was parameterized in a so-called dipole approximation for the form factors. And some of these were implemented in a public tool or so. But the situation was a bit really unsatisfactory from that point of view. So one can ask, does this really matter if you do collider physics? Do photons actually really matter or not? And if you would take one of these old determinations now at MPDF 3.0, and if you would look at something like Drellian production, so this black line is our standard normal Drellian production, QQ bar, giving rise to say a Z or an off-shell Z, which decays into leptons. Right? So this is the signal here. And then you see that if you go at large mass, you also have this photon-photon contribution. And according to this prediction, this from masses around 3 TeV, this becomes a dominant process, but it has a gigantic uncertainty. So if you want to constrain new physics at large invariant mass, this is really somehow a must-have. You must reduce this uncertainty. Also, if you look at precision physics at low masses, you see that this photon initiated is not so small anyhow. If you want to talk about percent precision, it's something that you have to control. So in general, so this is an example. It matters actually in many other cases. For instance, as I already mentioned, if you talk about precision, when you compute electroweak corrections to essentially any collider process, you have to include a photon in contribution. At the time, this missing, this large uncertainty on the photon PDF was such that this uncertainty was the largest uncertainty on two main Higgs production modes, vector boson fusion and associated Higgs production. We are talking about a few percent. I will show some numbers later, but this was really a dominant uncertainty. It's irrelevant, of course, if you do precision in top per production, vector boson per production, and so on. This is, for instance, again, a plot now showing the invariant mass of the 2W pairs again. You see the same behavior. This is a standard QCD behavior, and this is what was done in that paper, the photon-photon induced contribution, which becomes large but has this huge uncertainty. Now, some people that work in phenomenology will also remember that at the time, there was a lot of excitement because of the so-called 750 excess. So both collaborations, Atlas and CMS, reported an excess of a resonance with mass around 750 that decayed into photons. And of course, then people thought, okay, if the resonance decays into photons, you probably produce it by photon-photon scattering. So this is why a lot of people also got interested in the photon PDF at the time. Now this resonance disappeared, but this work remained. Okay, so how do we compute here the photon parton distribution function? So everything is based on actually exploiting deep inelastic scattering data. In fact, I should say electron-proton scattering data, not really deep inelastic scattering, because you actually look at all ranges of Q squared. But usually this kind of scattering, electron-proton scattering, this is a textbook process that we always discuss in the context of using the electron as a using this photon here as a very clean probe of the quark distribution functions inside the proton. This is how this is always thought of. But of course, the same process can be viewed as the electron probing the photon field inside the proton. Right? And this scattering process, electron scattering on photon, through an electromagnetic interaction is really very well known. And in the unpolarized case, you can encode everything you don't know in terms of two structure functions, which are called F2 and FL. So this scattering process can be written in a very simple form. Again, this is textbook material. You have two functions, F2 and FL, which depend on X and Q squared. They are unknown, but you can fit them from data, and everything else is really known. So in particular, this dependence on Y and X really depends on the fact that this is a vector-like interaction. Now, our model-independent photon PDF determination is based really on using this deep inelastic scattering data. And now taking a different process, I will be more precise by the process that we chose. But the idea is to take a hypothetical beyond standard model process and calculate it in two different ways. One, in terms of the structure functions, which I showed you now, and here everything is known. And the second one is to calculate it using a standard factorization as we have. So using a photon PDF and other PDFs. And then you equate two quantities, and then you can extract the photon PDF from this equivalence. So it's really a very simple idea. And I will explain it a bit now. So the first step is you look at this process in terms of, here you have an interaction. So let me show you directly. So the type of interaction that we chose is this, magnetic dipole interaction. So this is dimension 5 interaction, so it's suppressed by a high scale lambda. We take here somehow neutral leptons, a massless one and a massive, heavy neutral lepton. And the nice thing about this is that because it's a neutral, so there are somehow all higher order interactions are suppressed by the scalar lambda. So this, what you can compute is exact up to higher powers in 1 over lambda. So, okay, you can work out essentially, given the interaction, here this is a kind of Feynman rules you derive, you can compute this leptonic tensor here. These are the usual deep elastic scattering variables. And to convolute this with this hadronic part, which I told you this is known in terms of this F2 and FL. And here you impose the constraint that this object is on shell. Okay, so I think I already said this. So if you use neutral leptons and take lambda very large, everything is exact essentially. Yeah? And so the answer is exact up to 1 over lambda correction. This is the form that you can compute of this cross-section. Now you do the same, but now use the standard collinear factorization as we always do. So the master formula that I showed you at the very beginning. So you write the same cross-section here now using a standard parton distribution function. So you're summing over all partons in the proton. And you compute these partonic cross-sections here, which at lowest order involves a photon interacting here with this interaction. And at higher order, so you have also quarks and gluons here. And so this is the hard cross-section, the partonic one, written in terms of, so at lowest order you have the photon, the delta A photon means that this is a photon at lowest order, delta of 1 minus E, the photon carries here this interaction. And at higher orders, of course, you can have quarks that radiate a photon, so you get terms like this one. These are the charges of the quarks in the proton, and so on. And then at even higher orders, you also have two. So this is something that you can compute at higher orders. And so this is a bit technical, but I just want to say that typically, when you think about evolution, you always count alpha times a log of a collinear splitting as order 1. So quarks and gluons, we know they are order 1. Formally, they are of order alpha s times a log to all orders. So this we take as order 1. We know that the electromagnetic coupling is much smaller than the strong coupling. So somehow you can develop a counting where you count leading order everything that is alpha s log to the power n and alpha l log. So the photon you can think about it that it comes from a splitting of a quark times a collinear log. So this is our leading order term. And next to leading is anything that has an additional suppression, a power of alpha, S or alpha log, and so on. So what I want to say, this is a bit technical, but you can develop very formally a power counting for this, and then you can be very specific about which terms you want to compute or not. For instance, the counting where we think of alpha as alpha s squared comes from really phenomenology. One is about 0.1, the one is 1 over 100. Of course, you could also do a different counting here, but you can really precisely say which terms you include or not in your calculation. And so now I showed you these two parts, and then you equate them, and then you can extract the photon parton distribution function. So this is essentially the result that we obtain. Distribution function x times the parton distribution function is essentially given by this integral. So you saw on one part, you still have to perform this integral over z and q squared over these functions. But essentially, it's a very simple form. So what you need to know, what I want to stress is that you need to know F2 and FL essentially in the whole plane of x and q squared, because you have to perform these integrals here. Now, if you look at, if you take essentially the derivative of this, you should get the Altarelli-Parisi splitting functions, which is something that, in fact, we checked and we reproduced. And yeah, okay, so F2 and FL are extracted from data. At low q squared, these data are really non-perturbative data, while at high q squared, they can be obtained essentially from parton distribution functions. I will show really the plane and how we do this exactly. But the important point is that these are not calculated, but are really fitted directly from data. Okay, so this is essentially the plane now. So this is where you need to integrate your F2 and FL functions. So this is the accessible region. This part is simply not accessible. This is the elastic scattering where x is equal to 1. And then you see that you have a region that is really at very low Q squared. This region of very low Q squared is full of non-perturbative resonances. And there are fits here by class collaboration, for instance. Then there is this low Q squared but more continuous region. And again, this is fitted by a different collaboration Hermes. And then at high Q squared, this is the region where you really we can use essentially the D-Glab standard perturbative evolution. Of course, this line is set by us. We set this to 9 GeV, for instance, this separation between this line. This is arbitrary, and this is one of the sources of errors. You can change it a little bit up and down. And this somehow changes a little bit the result, and you call this... Yes, of course, yes. Yes. Okay, so this is now the result of the fit of the photon PDF, but now multiplied with some factors, powers of x, essentially to get something that is rather flat, right? To show, and what I want to show here are the different contributions from the different regions. So for instance, you see that at very large x, you're completely dominated by the elastic magnetic contribution. At small x, the elastic electric becomes more important. And essentially, all these other contributions are, you can essentially never neglect them if you want to have a precise determination. They somehow, high Q squared is what is called here PDF, is somehow dominant essentially everywhere. And this line, just indicative, shows you what comes from the region of Q equals 1. This shows you that both low and high Q squared data are really very important for this determination. And this is now what I mentioned. So we wanted to give an uncertainty to our photon distribution functions. And there are very different sources of uncertainty. And I want to discuss them a little bit now, very briefly. For instance, there is an uncertainty associated to the elastic component. So we took here again some data. These have an uncertainty, and you can look at how the uncertainty, the relative uncertainty here, that comes from the uncertainty on the elastic component. Again, you see here, somehow the elastic component is dominant here, but here, this is where it has the largest uncertainty. For the resonance region, for instance, we use two different fits by two different collaborations. You can use one or the other, and the difference you can use it as an uncertainty. And you see this is really dominant here at very large x. There is also an uncertainty associated what we call R. So the FL has the largest uncertainty. So R is actually the ratio of FL over F2 minus FL. And so this is this uncertainty here, shown here. There is an uncertainty associated at high Q squared to the standard PDF that you use to compute F2 and FL at large Q. And this is this uncertainty here. And so this is a bit technical again. This is a treatment of the upper limit in this integral that I showed. You can change it up to higher order correction. So this changing this limit is a way to estimate higher order perturbative uncertainties. And if you sum in quadrature all uncertainties, this is what we get, right, as a relative uncertainty. So you see that in a large region of x values, this uncertainty is of the order of 1% or below 2%. And so this is, now this shows the uncertainty on the photon PDF by an MPDF 2.3, for instance. This was before our work. So this is the relative uncertainty on the up quark, the strange quark, and the photon. You see that the photon was the parton distribution function with the largest uncertainty. And our work, it becomes actually the one that is best known, parton distribution function. This is also shown here. Now this is really x times f of x. So this is the standard shape of valence quarks, and this is the standard somehow more C-like distribution with this rise at small x. So this was again an NPDF 2.3, you see, with this huge uncertainty, and this is our determination. You see that this is not really compatible, but this has a really very small uncertainty. You don't even see the uncertainty band here, essentially. Again, this is now a comparison to our parton distribution function. So, for instance, you see this was an NPDF 2.3 and 3.0. Somehow they changed a bit their data. You see that their result from here to here changes quite a lot, not inside their own uncertainty. And this is our determination here with our uncertainty. So you see that at large x, they were predicting much larger photons than what there is actually. But at here, somehow, were even compatible within uncertainties. If you go instead at the small x, you see that here really these results are completely incompatible. So this uncertainty was here really underestimated. And even here, somehow these results don't really agree within the uncertainty. These are now our comparison to our parton distribution functions, again, that were available at the time. And more or less, you see that some numerically are actually closer to our result, like this one here, or even this here in a large range, but they still somehow did not agree within uncertainties. And in particular, at large x, they don't really agree very well. Now, this is the luminosity, the one that I showed at the beginning, the luminosity plot now. What is relevant if you produce a resonance produced by two photons. This was, again, the old plot, and this is now our plot with our uncertainty here. You see somehow the uncertainty is really much, much smaller now. And now one can ask the question, okay, but how big is how important is the photon in the proton? And I think everybody more or less remembers this number that half of the momentum in the proton is carried by gluons, half by all the quarks and half by gluons. Of course, this is a statement that depends on the scale at which you make the statement, but more or less at the electroweak scale, a gluon carries about 50% of the momentum, or actually here 46% of momentum of a proton. And now the photon carries about 1/100 of that, right? So it's about 0.5%, the photon content. So this is maybe the one number that you can remember out of this talk. This is also somehow shown here, right? And this again were determinations by different distribution functions. As you see, this is the red is our uncertainty on this number. And okay, I mentioned before that this uncertainty on the photon was one of the dominant uncertainty on a main Higgs production process. Now, to be concrete, the process was, for instance, associated Higgs production, Higgs in association with a W boson. So the non-photon-induced cross-section is about 90 femtobarn, with an uncertainty of about 2. And at the time, people estimated that this photon-induced is about 6 femtobarns, with this huge uncertainty of about 4 femtobarns. So this somehow this was dominating this uncertainty here. And now with our new calculation, we could show that, okay, this contribution is a bit smaller than what people thought. But most importantly, has now a really negligible uncertainty. The same is true also for other processes. This is really just one example that I want to show here. Again, you can look, for instance, at Drelian spectrum. And again, you can look at, so this is now Drelian as a function of the invariant mass. You know, high invariant mass is always of interest for new physics searches. So these are some uncertainties on data, statistical uncertainty. So this uncertainty will go down now with time. And so this is the ratio to the full QCD result. So essentially what you see here is that the photon-induced contribution is very important. You cannot neglect it even now at low invariant masses, otherwise you would not agree with data. And at high invariant masses here, with all determinations, you have these huge uncertainties, and now instead you really have a beautiful control over this kind of processes. Now, what happened after our work, very briefly? So this was the first paper, the one that is received their work here. We then produced a second paper with all technical details, much longer. And after that, essentially all global PDF fitters, so NPDF, MMHT, CT, and so on, they all used our method to include the photon PDF in their global fits. And they all have these versions, which they call LUX or QAD, which have now photon, our method fit, essentially. And then something else that happened. So, and then of course this photon-induced processes became of much more interest, but also something else that happened is, for instance, realizing that once you have photons in the proton, these photons can also split and give leptons. And there is interesting phenomenology associated to that. So first, as I said, LHC now can be seen also as a photon collider. This is true for protons, has also been looked at in the context of the ion collisions a lot. And so this shows really LHC that this is a very versatile experiment. You can do many things, new ideas can be followed up. So I will maybe not go into these details, but what I would like to talk about very briefly are also leptons in the proton. As I mentioned, so once you have a photon, the photon can split and give rise to leptons. Of course, the photon PDF, I already told you, is already rather small, 0.5% only. And the splitting also, you pay a price in the coupling. So lepton PDFs are actually very, very small. But you can compute them, and here are the lepton luminosities again. For instance, you can talk in lepton up luminosity, lepton gluon, and so on. And as a reference, this red is the photon-photon luminosity. So you see that some are actually very small, like the lepton-lepton luminosity and so on. But they can give rise to unique signatures at the LHC. So for instance, if at the LHC you see an electron and a muon and nothing else, without lepton luminosities, you would think this is some new physics. Lepton flavor violating new physics, but we know now that there are also signals that come simply from lepton PDF. So it's very important to compute this to be able to see what is the standard model background associated to that. They can also be used, and I will want to focus on just one slide on this, in new different BSM signatures. For instance, clearly leptoquarks. You can have now a resonance leptoquark production. So you a lepton from one proton and a standard quark from a standard quark PDF. And then you can produce a resonant leptoquark. Resonant production, as opposed to many other, for instance, a pair production of leptoquarks, is very nice because it rise to an invariant mass, some invariant mass peak. So if you look at the mass of the lepton and the jet, this is how a signature would look like. So of course you have a lot of backgrounds that you have to subtract, but this is a resonance, and these bumps are easy to see. And so this was used, for instance, to impose new bounds on Yukawa couplings, leptoquarks. So I come to my conclusions, and so the photon content of protons matters, both if you talk about precision physics and if you talk about new physics searches. I showed you one example, leptoquarks, but there are actually many examples that matters. The photon distribution function is difficult to compute because it depends on non-perturbative physics, so in the proton, right? But I showed you that it's possible to use perturbative calculations together with precision fits of structure functions to extract the photon density very precisely. And I think this is one of the really rare examples where we could have really a leap in precision from gigantic uncertainties to really percent precision without doing a super complex, very difficult calculations. It's also, I think, a nice example where progress in a different field, so achieving precision in the determinations of F2FL, which is essentially nuclear physics, has a big impact on high energy collider physics. So using this data and this progress, we determined the PDF with about 1-2% precision in a large region of X. And I showed you this opened up the possibility to do a lot of new physics, new studies using photon distribution functions. Thank you.
Next, let's invite questions from our audience.
I still want to understand how you take the Z boson exchange into account when you apply to momentum transfer above 100 GeV. And so can you still talk about the photon PDF? The Z is same.
Okay, so maybe I didn't understand your question correctly before. So here we are talking really about the photon PDF. You can also talk about the Z or the W PDF. And this, in fact, has been done. There is a study that has been, I didn't mention it here by Anish. But this is about the photon-only PDF. So when we do our calculation,
my question is that if you do this way above Z energy, it's indistinguishable. How can you separate photon from Z if its electric is a multiplet? Only low energy you can define the photon. High energy Z and the photon is mixed together. It's the standard model tells you Z is part of the photon.
Yes.
It's B and the W3 is the correct description at high energy and high momentum transfer. We have been working on this lately for the muon collider or something like extremely high energy. They are the same multiplets. When you're above the Z resonance, 100 GeV momentum transfer, Z is excited. Z will be excited. Numerically, it's small. Numerically, because the Z coupling is
it's small, and you can compute it.
Conceptually, you cannot separate. Conceptually, above the Z scale, the photon and Z are mixed.
So maybe we should discuss it a bit more in length. But I actually disagree. Maybe we discuss this more in length. Okay.
Yeah. Thanks for the nice talk. You have a plot for the photon distribution, which rise at small x, similar to how gluon distribution rise.
Yes, sir.
In the case of gluon, people believe it will not continually rise. There will be a regime where gluon will saturate. In the photon case, I also think it shouldn't always rise. So what do you think would happen when you are looking at very small x? What mechanism that turns the curve?
So, okay, this rise of the photon at low x is driven by the rise of the C quarks at low x also. So the gluon has this shape that rises, but also all C quark distributions have the same. And the photon, this inherits this behavior. And you are asking if there are issues about kind of saturation effects for the photon distribution at very low x. Was this a question?
Yeah, I'm worrying that the photon rise too fast at small x. But
are you worried for whether there are saturation effects, or why do you say too fast? I mean, the gluon rises more.
The gluon, yeah, but in the case of gluon, people think it will not, at some point, it will saturate.
Yes.
Yes, that's
here. No, but here, I mean, the photon is allowed to rise. I mean, there is no issue related to the rise of the photon, right? I mean, as long as you conserve momentum sum rules, and the photon is allowed to rise. There are no issues here.
Okay. Yeah. Okay. Thanks.
Okay. So,
are there any other questions? Oh, Christophe.
Will the FCCHH data useful for anything in this business or not?
For FCC?
FCCHH.
Well, of course, yes. I mean, no, I mean,
quantitatively, I mean,
I think everything, and now everything is much more focused to LHC, but then everything translates. So everything from precision Drelliana, diboson, top. Yes.
Let's forget about that before. I mean, just.
Why do you want to forget?
It will be dead. No, but
no, of course. Yes. But okay, now maybe this didn't say very clearly, but now this is part. These PDFs are part of the standard PDF. So this is done. It's studies people are doing actually, and they are part of the FCC studies now.
So originally in your model, you have some electron-proton. Then you have a scale lambda, and I don't understand what did you do with the scale.
So this is okay. It's also another point that I didn't mention explicitly. Scale lambda cancels clearly because it's so you're equating two expressions and both have this scale in front. So scale lambda is simply to preserve dimension. You have dimension 5 interaction, so you put a 1 over lambda. And of course, if you change process, and we did it, we looked at a different process, you have to get exactly the same out. So everything about the process-specific part has to completely cancel out. And the fact that these leptons are neutral is useful because you can do higher orders without computing loops that anyhow would cancel, and you know that they have to cancel on both sides. But,
yeah, wondering if you could repeat what this resonance region is and why, for example, it dominates uncertainties at large X. What is the resonance contribution again? Could you describe it again?
So if you look at the plot of the R ratio in any QCD book, you see that at very low Q squared, this is you have all these raw resonances, the resonance production of light resonances.
Yeah, but that's for time like that happens in the formula. Your formula that writes the photon PDF as an integral over F2.
Yes. So when you're
saying that this resonance also are in this F2?
Yes. Yes. So F2 is the parameterization of.
For R, it's a time like Q square, but here it's a space like Q square. And I'm not sure I understand. I'm not sure I see the resonances here.